So, hi everyone, how's everybody doing today? You guys still have some energy? I hear you guys have been, what was that? A little, okay, good. Yeah, I hear the boot camp has been tough and hopefully exciting. So as Joel said, I come from ODU, which is where I teach, and there's actually 6 of us that are in the particle/nuclear theory group there. And all of us also have a joint appointment with Jefferson Lab. And Jefferson Lab is Old Dominion is in Norfolk, so here's some of the more pretty sites of Norfolk. It's pretty, very pretty, I would say. And then Jefferson Lab is in Newport News, and this is a medium beam accelerator. They accelerate our electrons, and these are crashed onto nuclear targets with the purpose of studying the structure and properties of nuclei. So I'm not, even though I'm in the lab, I have nothing to do with experiments. There's a theory center in there, and we all carry out QCD-related calculations that are hopefully in contact with the lab, but not necessarily. I mean, we might have connections with other labs. And there's a logo of my collaboration, the Hadron Spectrum collaboration, which actually we have a junior member in the audience. So I'm going to be showing you some results as I proceed on calculations that are being done by our collaboration. In designing this talk, I wasn't quite sure the spectrum of backgrounds of everybody, so I kind of have a lot of fluffy introduction and motivation, physics motivation to why we care about these things within the QCD, trying to study these things directly from QCD, and what are we trying to understand. And then I had some fairly technical stuff towards the second half, which I'm happy to skip over if people just feel a little too overwhelmed, but I figured I would show as many details as possible so you can use this as a useful reference for you in the future if you want to learn about it. But I'm happy to skip and talk about whatever you guys want, and so we'll gauge your interest as we go on, okay? So I'm going to talk to you about scattering, which also you can think of it as another word for few body physics. So I'm basically interested in systems that are composed of 2, 3 hadrons or so. Today I'm only going to focus on 2 hadrons, and this has 2 broad motivations, two motivations that fall in the broad categories in modern day nuclear physics. The first is QCD spectroscopy. The second is low energy nuclear physics. So let me start with the motivations of what are the types of questions that we're trying to understand from both sides. So on the QCD spectroscopy, the motivation is to do just that, to determine the QCD spectrum and trying to compare it to experiment and trying to understand the manifestation of QCD at low energies. In fact, this is the very first thing that anybody does when you write down a theory. If you write down electromagnetism in quantum mechanics, the first thing that you try to do is study a spectrum. The QCD spectrum, even though we've written down the Cassini Lagrangian decades ago, we still don't understand how the spectrum manifests itself directly from the underlying theory. This is an outstanding challenge. And just to convey how challenging this is, the simplest state that we can think of in QCD, the most familiar ones that we know, the simplest ones that we can write down are the nucleon, which is a state that is composed of color singlet combination of 3 quarks, and then also the pion. The pion is the lightest of all QCD states. But these fall under a category, each one of these has a variety of states that have the same quantum numbers. Just like the hadron has a tower of states, the nucleon also has a tower of states. The second state that appears is given, the name that has been given to it is a Roper. Roper was the first to point out that there's a state present here. In the pion, there's one that is called pi 1300, and these towers keep going on and on and on. Okay. The reason why these are challenging to understand directly from QCD is twofold. One, QCD is non-perturbative, and you guys have been thinking about this. Second, the way that these manifest in QCD are as resonances. These states are not stable; they decay onto other lower line states. And so, for example, the Roper decays onto a state of a nucleon and a pion with any range of possible intermediate energies. and then it can also as well decay onto a combination of nucleon, pion, and another pion. So it can decay to 3 particles. And so this makes the experimental observation of these quite challenging, and similarly it makes a theoretical study of it quite challenging. To be able to study this, we would have to have a framework that is non-perturbative in QCD, and where we can study the amplitudes of 2 hadrons and even 3 hadrons non-perturbatively, and also allow for the coupling to emerge. So this is a quite challenging prospect for us to do, and nobody has been able to do this so far. So this is an outstanding problem. And so this is, I'm going to give you some sense of all the steps that we're taking to be able to address something like this. Similarly, the pi 1300 also decays to a rho and a pion, and then the rho itself is an unstable particle that then decays to other particles. And so this is also quite challenging mess. And so what I want to try to convince you today is that this is a hard problem, but we've been systematically addressing each bit of it bit by bit. And although when I started my PhD, people would say that things like this were outside of the reach of what could have been done, and I started my PhD maybe 10 years ago, or a little over 10 years ago. And what we've been able to convince at least ourselves and part of the community is that these are no longer impossible. They're very hard, but not impossible. And so I'm going to tell you about these prospects. So how do you access resonances in experiments? So even though I'm not because I'm not an experimentalist, I can give you just a cartoon sketch of how these are accessed experimentally. So for example, let's say that I wanted to study an excitation of the pion like this. Well, the pion is unstable. You can't actually have an experimental target for a pion. But what you can have is an experimental target with a nucleon. The nucleon, qualitatively, you can think of it as being surrounded. Its shape is given by a cloud of pions. You can have, and so you can have these pions be intermittently on shell for a little second. And what we hid these pions, so in the GluX experiment in Jefferson Lab, these nucleons are hit with a photon beam. So what is accelerated in JLab are electrons, and these are then these emit photons, and these can then couple to hadrons. So this photon can then excite this pion onto an intermediate excitation. In this case, it could be the pi 1300, or it could be something similar like the rho. And then this state lives for an instant for 10 to the negative 23 seconds, and it quickly decays onto hadrons. And it is these hadrons that then you detect. So you see the manifestation of this intermediate state from the scattering of the final state hadrons. One thing that we want to be able to do also theoretically is to be able to probe these states and understand them directly, and try to understand their structure and understand how quarks and gluons come together to combine into these states. And so that would require to be able to probe them with some other current, say an electromagnetic current or so forth. And this is outstanding. This is remarkably challenging experimentally, and it cannot be done. But in principle, we can do this on the lattice. And so the goal of the broader lattice QCD spectroscopy effort is to be able to find conformations, understand the production mechanisms, identify the decay processes of these states, and how these couple to scattering states. And so these are the types of things that we're trying to do directly on the lattice, but we can do a lot more than experimentally is accessible. We can actually probe these states and be able to start painting some picture of what these states look like. And so examples that I'll be talking about are states that have the quantum numbers of, say, glue balls. So this is something that is solely QCD-like. There's no photon ball in QED. So in QCD, you can have, in principle, states that have just pure gluons coming together. but you can also have things like QQ-bar as well as QQ-bar mixing with gluons, and then also you can have molecular type states. Just like how you can have molecules in QED, in principle you can have molecules in QCD. And in fact, we see these in nuclei. There's these so-called halo nuclei, which are composed of a compact, say, helium-4 state that is surrounded by neutrons that are orbiting around it. So these molecular type states, these molecular analogs do exist in QCD, and in principle they also exist in the excited spectrum of QCD. And so there's a rich spectrum for how we're starting to categorize states in QCD, and of course they first can be categorized in terms of baryons and mesons, but even further they can be categorized on how their Fock space looks like, meaning what is the minimum content of quarks and gluons that are needed to construct these states. And so there are the conventional ones, which are for example the nucleon, where you just have 3 quarks, which that's the minimum number that you can give associated with the nucleon. Of course, there's some non-perturbative stuff that comes in and makes these some complicated states. On the meson sector, the analog of this would be the pion, which is just made out of QQ-bar in a color singlet. So one has red color and the other one has anti-red. But then there's more unconventional states. And the reason for searching for these unconventional states is because they can give us further insight into the low energy manifestation of QCD. And so perhaps you've heard about the searches for pentaquarks in LHC. Has anybody heard about this? Roll it out. This, okay, good, okay. Yeah, so these were discovered first in 2015, and these are states that the minimum number of quarks that can be arranged are where you have 3 quarks in a color singlet, and then you have a QQ-bar type combination. And these are tied up, of course, by some non-perturbative nature. Of course, you can also have molecular states where you have color singlets that are attracted to each other. And an example of this that we know beyond the halo nuclei is also the deuteron. The deuteron, which is the lightest of all nuclei, is a proton and a neutron that are loosely bound. So people have long-standingly, Weinberg actually have proposed that this can be thought of as a proton-neutron molecule because it's loosely bound with a radius of roughly of 2 Fermi. So it's quite big by QCD standards. And then you can have more exotic combinations of 3 quarks and something that is like glue ball-like. These are called hybrids. In the Masonic sector, you can have something like glue balls, as already said, and you can also have tetraquarks have been observed, and so forth, hexaquarks, and everything else. There's various searches in JLab, primarily in the class 12 and GluX experiments, and also abroad. I mean, there's a big experimental effort in Europe as well as in Asia and so forth. Okay, so let me tell you a little bit about some open questions that we're trying to address, and I'll show you some calculations with some of my collaborators on this sector. So one sector that we can zoom in is the sector that has the quantum numbers of the QCD vacuum. So it has 0 plus plus, so meaning the angular momentum is 0, parity and charge conjugation are plus, okay, positive. And so this has the quantum numbers of the vacuum. This is a particularly interesting sector because it has many states that have been observed experimentally, and all of them are equally puzzling for different reasons. So these are called F0 500. This is historically known as a sigma. Then there's a F0 980 and so forth, a bunch of F0s. Basically, the way that the particle data group is labeling these states in general now is they will give F0 is telling you that the quantum numbers are 0 plus plus, and then the number associated with it is giving you a rough estimate of its mass. Okay, and these numbers shift because experimentally these numbers shift. We get better and better data and eventually resolve a different mass. Okay. And so the kind of questions that appear is that, for example, the F0 500, the sigma, that historically was known as a sigma, there was a long-standing puzzle as to whether this state existed or it was just an artifact of experimental analysis. There was good theoretical evidence to suggest that it was there, and now we have a lot of confidence that it's there. And also, people have proposed that perhaps this is a conventional state, while other people suggest that it is a pi-pi-like molecule. The F980, which is the next one that appears, has also been suggested to be a molecular state, but not of pi, but of kk bar that have the same quantum numbers as pi. But also other people have suggested that perhaps this is a potential tetraquark. So these would have very different structure, right? One, you would have two loosely bound hadrons, and another one, you would have a very compact 4-quark combination. And then, of course, are the famous possible glue balls, which is perhaps the longest standing prediction from QCD that hasn't been observed. And so why are these structures hard to disentangle from experiment? Well, the reason why the F980, so let me just think about this one example. The reason why the F980 has been long suggested to be a kk bar-like molecule is because it lies just below the kk bar threshold. And so it seems quite natural. It actually seems like the deuteron, which lies just below the proton-neutron threshold. And so people have made analogs there. But unfortunately, it's a resonance. It also decays strongly to pi. And so it turns out that the coupling that it couples to kk bar is the same as pi. And so this picture starts to wash out. And so it appears that there's no obvious systematic probe for us to be able to distinguish these two pictures. But we're building quantitative measures that I think will be able to resolve this in the next few years. And so by the end of today's lecture, I'll show you the first results of the F980 and its manifestation on the lattice. Okay, so that was my broad introduction to QCD spectroscopy. Now let me give you a shorter but equally broad motivation for nuclear physics. So nuclear physics, what I mean here are thinking about bound states of protons and neutrons, or interactions between protons and neutrons of any combinations. This is something that is, part of it is remarkably well studied experimentally, so it would be unlikely that Lattice is going to be able to say something as accurate or as precise as experiments. But here, what Lattice is motivated in is to access things that are experimentally inaccessible, or that are rather challenging to study experimentally directly. One example of this, also I should say, if you guys want to stop me at any point and have any questions, please do. So if there's anything that I'm saying that doesn't make sense, just stop me and I'm here for you guys. Okay. All right. Okay, so here, the one example of the types of things that we're interested in, and I mean really the broader Lattice community, is to study things that are experimentally inaccessible. So the simplest thing that I've been interested in, and there's already some ongoing calculations on this effort, is to study the reactions that happen, for example, in the sun. So how does the sun get fueled, or any star by that mean? Well, it's a bunch of nuclear reactions that are taking place in the sun that leads to a spectrum that we see being emitted by the sun, and that's what leads to the evolution of stars. The simplest of all reactions that we can cook up from the standard model is where two protons fuse into a deuteron. Right? The sun or any star to first approximation is just a bunch of hydrogen that has become unbound, and so you have a bunch of loose protons. And how do they then fuse to become heavier nucleus? The first reaction is this one, where you have two protons coming in. One of them goes through a weak transition, emitting an electron and a neutrino, or a positron and a neutrino, and it transitions to a neutron. And then it fuses. Then once the neutron is there and it's present, it's allowed then to, via the strong interaction, to form a bound state of the deuteron. There's no bound states of protons and protons. There's no bound states of neutrons and neutrons, as far as we can tell in reality. So this is the simplest nucleus that can occur. And so one thing that we'd be able to want to study on the lattice is this reaction, which is experimentally inaccessible. So it's QCD plus, this is a really interesting process, because you have the protons, which are charged, so they're going to be interacting via not just the strong interaction, but also via the electromagnetic, right? They're going to be emitting photons. For this transition to occur, you have to have the weak sector present, and then they're going to fuse via the strong interaction. So this kind of, is a bit of a low energy holy grail, right? I mean, it encompasses QED, weak interactions, and strong interactions all in it. And it's the birth of all the nuclei that we're made out of, right? Once you have the deuteron, you have two deuterons, and they can fuse to helium. Once you have helium, you can have a 3-alpha process and start combining into carbon, and then there's life, right? So these are the types of things that we want to be able to see. The standard model is a standard model consistent with the formation of life, broadly, right? So this is, you might think of it as an academic exercise, but it's a quite interesting and powerful academic exercise. But obviously this puts quite a bit of constraints on the reactions that occur in the evolution of stars, so that is information that can then be fed into astronuclear physics. So, but also there's a lot of tests that are trying to be done on the standard model, and it turns out that modern day tests of the standard model, at least in the States and many other parts of the world, involve nuclear targets. So you probably have heard of DUNE, so precision measurements of weak reactions involving neutrinos. The targets are nuclear. Another one that is kind of I'm particularly interested right now because I was just in a workshop in Italy is neutrinoless double beta decay. And so here, there's a process where you just put in a whole heavy nuclei and you wait for them to go through a double beta decay process. So double beta is a process where you have neutrons and they transition into, or a single beta process is a process where you have a neutron transition into a proton emitting an electron and a neutrino. But neutrinoless double beta decay is a predictive process where this transition would occur, but then you would have no neutrinos being emitted. And so if you observe this, you certainly get a Nobel Prize. And you don't need QCD or Lattice people to, well, that's not actually true, but to first order, you don't need Lattice or nuclear physicists to tell you anything about this. If you observe this reaction, that's already giving you information that there's a mechanism that is beyond the standard model. But if you want to be able to understand what is the actual mechanism, you need to understand the QCD part. And so there's a broad effort that is being carried of trying to constrain these types of matrix elements from Lattice that can then be fed into few body and many body calculations and be able to constrain the QCD part of these reactions. And so we can understand if this reaction occurs, what does that mean for our constraints of beyond the standard model physics? And so this is, I think, is quite interesting because, I mean, it requires knowledge of QCD, QED, weak physics, but it also would serve as input to beyond the standard model. Hence, why is testing the standard model? And so the last thing that I'll say about these two things is that although these two physics motivations seem separate, that is QCD spectroscopy and nuclear physics, they really are two sides of the same coin. They really are, broadly speaking, just few body physics. And the tools that are used in studying one are the same tools that will be needed to study the others. And so in my PhD, I was mostly interested in the nuclear side, and I've moved on to the spectroscopy side, but always, we kind of go back and forth. And so we collaborate across both lines. And so with that being said, let me give you now a last introduction, a broad overview of what few hadron systems, how do we actually study these broadly both, and how do we connect QCD experiments and a little bit of scattering theory, which I'll start introducing in a little bit. So historically, experimentally, what you obtain are cross-sections. So this is a little example of cross-sections. This is pi going to pi. This is old CERN Munich data as a function of energy. And so we've developed scattering amplitude analysis or theoretical frameworks for describing these reactions, and that allows us to extract scattering amplitudes from experiments and then be able to identify the spectrum associated with these states. And what I'll try to convince you is that the spectrum is hidden in these cross sections, just in a non-trivial way. Historically, QCD has been outside of the scope of what we can access. We haven't been able to access amplitudes directly from QCD, but so instead we've resolved to use models or effective field theories that are an approximation of QCD at certain regions, and this is what has allowed us historically to obtain amplitudes and compared to experiments. But of course, now we have lattice, and so lattice is in principle non-perturbatively, and in principle we can access these same reactions, but it has turned out to not be accessible directly. So we have to go through an intermediate step. And so the observables that are obtained on lattice QCD are finite volume quantities. This might seem like a nuisance or maybe not that important, but it turns out to be the biggest challenge that we have, is trying to understand how do we connect these finite volume observables to what we desire, which are infinite volume scattering amplitudes. And this goes to Joel's point, and I'll be fleshing this in quite a bit of detail. And most recently, we've been able to also construct observables that are outside of the scope of what experimentalists can reach. And this would allow us to study these reactions, like, for example, PP fusion and so forth. And what I'll focus on today is this connection. I'm going to largely assume that I've done some lattice calculation and I've obtained something, and I want to get some meaning. I want to put some meat into understanding of what is being obtained, and in particular, I'm going to focus on how to extract these amplitudes while showing you some examples. Okay, so assuming there's no questions at this point, let me start by giving you just a brief reminder of what are the key building blocks of lattice QCD. So lattice QCD can be identified by a series of bullet points. First, I grab my theory, whatever it is. In fact, it doesn't have to be QCD, right? Any lattice field theory. And I can just grab that theory and first Wick rotate it. This is a necessary step so that instead of doing calculations in a Minkowski spacetime, we do calculations in a Euclidean spacetime. This is necessary so that at the end of the day, what we have to evaluate is some big integral over all the possible degrees of freedoms, which is outside of the scope of any present numerical tools that we have. But instead, we can evaluate it approximately using statistical tools, in particular Monte Carlo sampling. To define the theory rigorously, we need to introduce a UV cutoff. And this is a lattice spacing. This is the lattice spacing, right? And this is just the smallest separation between all points in space-time, and so it's a short distance regulator, and so in other words, it's an ultraviolet one. But necessarily, we also have to truncate our space-time. This is so that when we write down our theory, we're going to write down QCD in a representation in terms of matrices that we can then just eventually, at the end of the day, all we have to do is just matrix multiplication in our calculations. But the size of these matrices grow with the volume, right? And so I can't simulate a infinitely large space-time because my matrices will be infinitely large, and I couldn't do anything with that. So I need to truncate it. So that means that I've had to introduce an IR regulator. So I've done two things. I've introduced I introduced an IR regulator for necessity, okay? And so now L is going to be the length of my box, and although we do calculations in a three-dimensional box, yes?
What do you mean by IR regulator?
Infrared. So I mean that it's a low energy. So it's giving you the maximum separation between any two particles. It's now going to be L. Or it's going to be of the order of L. And so that's a long distance cutoff, which is a low energy. Long distance corresponds to low energy, and that's what we call infrared. Okay. And the other one would be ultraviolet, which would be a short distance regulator. And so, and you can't see it? Okay, it's a little faded. And so when you put things in a box, you need to put some boundary conditions. You have to say, what happens to the particles when they reach the box? There's a lot of freedom actually on how you do this. The most convenient one that we use are periodic, and these are everything I'll be talking about today is periodic. You can use other ones, but things just get a little harder, or just specific to the boundaries. And what you can imagine that is not happening here, I don't know if you can actually see it, it's just too faded, is that if I have if I have periodic boxes, then what that means is that the nearest, as this particle goes to this side, as this particle moves this way, let's say, then its mirror image is going to start creeping in into the other side. Okay? And then furthermore, this mirror image of this one is over here. And so let's say that if I want to move this particle over here, well, it's never going to be ever free. It's always going to be near some other particle, either its mirror image or its partner's mirror image. And so what this does is that we never have this notion of free particles that are outside of the range of the interactions. And so the basic assumption that we make when we think about scattering is that you have some free particles that are, have some mass and energy and so forth, and then we accelerate them towards each other, and there's a region where the potential between them is non-zero. And then that region is where they interact, and then stuff happens. We don't know what that stuff is, but then the particles emerge out, and then we detect them again to be free. And the encode of how they interact, we have observables that tell us exactly how to understand the interaction in between. We introduce observables that give us a metric of how they interacted in that region. But the basic point here is that we don't ever have free particles, and so therefore we don't have any notion of scattering. Once we introduce a finite volume, we can't do scattering directly. And so this is a challenge that we hope to address. And then finally, you have to do calculations of your quark mass, try to tune them to experiments. But I would argue that here, although when you hear a lot of lattice talks, a lot of people are doing calculations away from the physical values of the quark masses, I think it's quite interesting actually to do calculations away from the physical point, because those are indeed experimentally inaccessible, and it gives us a better understanding of the the dependence of observables in terms of the parameters of the standard model, and it at times can give us a better intuition about the theory than experiments alone can give us. So this is an advantage, I would argue. And then you eventually have to do evaluations of correlation functions and so forth. And so I'm gonna, if this is not familiar to you, I don't know how much you've covered correlation functions, but I'll give you some of the basics in a few minutes. So the last thing that I'll give you in my introduction is a status report of where things stand now on just on the interest of few body physics or spectroscopy, if you will. So it turns out that at this point we're at a level where Lattice has made a remarkable level of progress, and for simple properties of QCD stable states, namely protons, pions, and so forth. These calculations have reached now the level of being done at the physical point, including even some that are below quark masses that are lighter than experiments. So that's a remarkable achievement. Calculations are being done with non-degenerate quark masses where the up-down strange and sometimes even the charm are taken into account dynamically and are allowed to be distinct from each other. And some people are even doing calculations with dynamical QED. This is a really exciting new venue where calculations are being done. And just to illustrate this point, here's a calculation of the proton mass as a function of the quark masses or as a function of the pion mass. And this is a summary of various different calculations using different actions, different methods, different, that's basically it. And different techniques in general, and you can see that everybody agrees. I mean, there's no tension anywhere really, and so this is a remarkable achievement of the field. And this is one point that is done below experiments. So obviously, the uncertainties are big, and they end up growing as you get towards the physical point, but this is something that you can beat down with statistics. So I would say this is not a problem. The frontier, one of the many frontiers of Lattice is not this sector of, where now there's many different frontiers, ones that involve trying to understand more complicated observables of simple states, and I think you heard some talks, at least from Sergey and others, on trying to study structural information. This is an ongoing, very exciting area. One of the frontiers is the study of multi-particle physics, where we're trying to extract our scattering amplitudes, reactions, and bound states and resonances. And this is still a lot of formal development is being carried out here. We're still trying to figure out how to do these calculations, and more is needed. We've done some benchmark calculations, and these are mostly exploratory and proof of principle, and they're being done not with all these different check marks yet. So we haven't reached the precision era, which means that there's a lot more to be done. So which means that if you want to join this field, this is a field where there's still a lot of problems to tackle, and a lot of smart people are needed. So that's my pitch for you guys. And so I figured I would bring my dog along, and so she's a good tool for me to shut up for a second and give you guys room to ask questions. Also for me to sip some coffee. The nucleon? The nucleon is a function of the pi mass. Yeah. And I should say that I think at this point, maybe Joel or somebody else might correct me if I'm wrong, but at this point, there's no meaningful tension between lattice and experiment. Of anything that lattice has done, carried out all the systematics of one observable, done physical quark masses, continuum limit, infinite volume limit, have a robust analysis, in a comparable level of rigor in the experiment. There's no tension at this point. So that's quite an achievement. I mean, I think that this is basically to say that there is a tool that we trust, and now we want to try to build upon it and do more and more complicated things that are outside of the scope of what we can do now.
Yeah, so one of the things related to quarks, there was a really nice study done a couple of years ago where they did the neutron-proton mass difference.
Yeah.
They got a thing on.
Yeah, the BMW calculation.
Yeah, they were able to incorporate the key defects and the mass splitting effects.
So this is one of the examples of calculations that I say that people are doing dynamical QED. This is a very challenging thing to do for multiple reasons, and people are really doing a beautiful job of dealing with all the systematics that come in when you put in QED on the lattice. And as Joel said, there's now calculations that have been done that are quite precise of the proton-neutron splitting, as well as I think it's like the sigma plus sigma 0 or sigma. Also some other baryons splitting, definitely the doubly charm cascade mass prediction is there. So there's also predictions that have been done on the lattice that haven't been confirmed from experiment yet, right? So yeah. Yep, everything is Euclidean so far. There's ongoing efforts to do things in Minkowski space-time. Those are remarkably challenging calculations because you don't have simple Monte Carlo sampling. So there's techniques that... okay. Yeah, so I think there's people associate the word with dynamical with real time. I associate dynamical with non-trivial dynamics. So just because you're doing calculations for example, if people that are familiar with standard field theoretical tools, if you study one loop diagram of scattering, you write down your loop in Minkowski spacetime, but then you Wick rotate everything to Euclidean, and that's where you actually can do things like dimensional regularization. So just because you do things in Euclidean spacetime as a tool doesn't mean that you aren't accessing the same observable in a Minkowski theory. So this incorporates all the dynamics, doing real-time observables, so things that actually depend on the time signature is challenging on the lattice, but it's not impossible. There are some non-trivial. You can do Compton scattering, for example. So, yeah.
Can you give an idea of what Minkowski space-time is? What's the difference between that and...
Yeah, sounds good. Okay, so what that means is that time and space are being treated differently. So if you have, for example, so a 4-vector in Minkowski, well, both in Minkowski and in Euclidean space-time, I can write it down like this. And so the dot product between two vectors, for example, with this vector with itself, there's a metric that tells me that the first term, when I just multiply with itself and nothing else. But then the spatial, so this is called, I would refer to this a temporal piece, and this is a spatial piece for semi-probably obvious reasons, and this is a 3-dimensional vector. But then the spatial piece comes in with a relative minus sign, and then I just multiply the dot product of the two. So this is Minkowski, okay? So this is a Minkowski signature. Minkowski, well, no point spelling it because you can't see it over there. While Euclidean, I'm not gonna spell anything because I'm gonna misspell it. You would have the same thing, okay? But now there's no distinction, there's no need for a matrix. So here I'm just gonna do x squared, and so here what you would have is that the sign that appears in the temporal piece is the same sign as a real part. Well, that's what is meant. So then Euclidean means time is just a 4th dimension of your 3-dimensional box, while in Minkowski, time is a whole different animal. And so you might worry that by doing calculations here in Euclidean spacetime, you're not accessing the same observables that you are in Euclidean. But that's actually not the case. And in fact, at this point, I can so I have some more technical stuff in the next areas, but we can actually slow down and try to convince you, for example, that the spectrum, the mass of a single hadron using Euclidean correlation functions and Minkowski correlation functions is absolutely the same. There's really no difference, even though you might worry about this. So I skipped over this point, but I'm happy to go back on it. So why don't we put a pin on it? That's the right expression, right? Put a pin on it. And so we can come back to this if people have some confusion about this. Okay? Back to Jazzy. No more. Okay, so I have an outline for the rest of today that I'm going to be slowly building off of it. Okay, and we can stick to it as much as we want, and we'll maybe deviate from it. So to go back to this Euclidean versus Minkowski question at some point. Well, actually, this might come up right here. So I figured, I don't know how much you have covered on the notion of correlation functions. Not much at all? Okay, so we can, and I should say, I know that this is mostly a numerical boot camp, but although I do numerical stuff, I'm kind of the numerical runt of my collaboration, and I mostly do formal stuff. So I skewed things towards the formal side. So if you guys, if there's anything that we just want to skip or slow down, I'd be happy to do that. So okay, so correlation functions. What do we mean by this? What we mean are what we measure on the lattice. The simplest correlation function that we evaluate are so-called time-dependent correlation functions. And so what this is these are. So who has seen quantum mechanics here? Everybody's seen quantum mechanics? Anybody seen field theory? Okay, maybe a quarter. Okay. Actually, here, if you allow me, let's take a little detour because I have some slides on and try to convey what correlation functions are in the context of quantum mechanics, and then we can go back to the quantum field theoretical definition. Is that okay? Okay, good. So there's this different summer school that I taught at last 2 years ago or so, where people were interested in scattering theory. Okay. I haven't looked at these slides in a little while, so I might have to digest them as we go on. But I think you'll be patient with me. Okay, so are people familiar with the path integral representation of quantum mechanics? All right, wonderful, great. Okay, so correlation functions in quantum mechanics are, imagine a world where, let me forget about QC for now. And so I'm going to imagine a world where quarks are free to propagate. And I want to evaluate the correlation. I measure a quark at some point x1, t1, and I want to measure the probability of finding it at some xf, tf. Okay. And so in quantum mechanics, this is just, I have some initial state, xi, right, is over here, and I want to time evolve that to ti, and then I want to annihilate it with some state in some position xf and tf. Okay, and so I can just use the Schrodinger picture for evolving the states, and so all I have to measure is this probability. Okay, just measure this overlap. And so okay, so then I can write this. Did I drive this? No, I didn't. Okay, so the path integral representation of quantum mechanics, which if you haven't derived it, it's just by inserting a complete set of states by dividing this evolution into small little intervals and inserting a complete set of states leads to a integral where I'm integrating over all possible paths that I can take from the original point to the final point, and then the measure associated with this is e to the I, the action. And then it's just the classical action. And so the path that minimizes this, that minimizes the action is just a straight path. It's what is called the classical path. But in general, I can have any possible, quantum mechanics allows you to have a bunch of different paths, and that's what you're integrating over here. And so in deriving this, what we did is exactly what I just said. You divided this into a bunch of little time intervals. And so what this measure really means is discretize these time intervals and then evaluate the possible values that x can take at each one of those times. And this is what this picture is telling you. So I take a little time, and then I can have to integrate over all possible x's here, and then all possible x's here, and all possible x's here, with the action having a different value for each one value of x. Okay, so this is how you derive this analytically. And then you said, I'm going to take the formal limit as at goes to 0, and I got this. Right? Lattice is saying, don't do that. Don't take that limit analytically, rather take it numerically. That's the basic idea. And so then, how do we then evaluate this numerically, this integral? Let's say I wanted to do it numerically. Well, what I can do is just have a discrete values of x's, and I just sample over those different x's with some appropriate measure, right? And I can do something more clever, but I'm going to take just different discrete points and just evaluate over all possible intermediate discrete points, and then eventually take the limit as a separation between meshes in X go to 0. Instead of doing this analytically, you can just do this numerically. And so this is basically the idea of lattice. So you can just evaluate correlation functions. So what is the probability of finding some state that was initiated at some time with that is that you annihilate at some later time and space. So this is the idea of correlation functions in quantum mechanics. And so in quantum field theory, what you have is something different. You're not just measuring the correlations between one point in space-time and another, but what you are allowing is you're evaluating different possible configurations that your particles can live in as well. So you have some, for example, I have two quarks that are submerged inside of a pion, and I create some pion at some point in space-time, and I annihilate it in some other possible point in space-time. Okay, they can take some pathing going from one point to another, but also the way that they look like as they're going through this path can also look quite differently. Okay, so let me see what I said. And so then the point is that here what you're evaluating are not just all possible paths, but you're evaluating all possible ways that these fields can look like. And by fields, really what we're saying is quantum field theory, all it does is that it grabs particles and it upgrades them to some field, and then the particles are just excitations of this field. Okay? And so now all you're doing is just summing over all possible configurations that these fields can look like. So at some given point, I'm just getting a little snapshot of what the field looks like. And so here you can say, oh, it looks like nothing, 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 quark, nothing, nothing, quark, nothing, nothing, nothing. Okay, and same thing here. So then you say, okay, here's nothing, 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 gluon, quark, quark, nothing. That's what we mean by basically just having different possible configurations. And so then what you end up just doing is integrating over this field configurations, again with the same weights. And this phi is just a proxy for the possible fields that are present. The action is the same, so it's the same action, but typically it's not written in terms of the integral of the Lagrangian, but rather the integral, the four-dimensional integral of the Lagrangian density. And so you're sampling different configurations at different points in space. Okay, and so again, the idea of lattice is to then say, I'm going to grab this field theoretical prescription on particles, and I'm going to put it into a discretized space-time. And so this, let's say, the simplest thing that I want to evaluate is a path integral for just the fields, and this is equivalent to a partition function or similar to a partition function in statistical mechanics. And so what I want to evaluate is all the possible fields, all the possible values that the fields can take at all possible points in space-time. Okay? And so really what this measure means is I'm going to grab the field at each point in space-time and integrate over its value. So here I have some field associated, for example, a quark at this point, and I'm going to integrate over all possible values that it can take. And this is, I can measure what is the probability that there will be a quark here or not. That's essentially what the field is tabulating. And then I do it for another point and another point, and I do it for all my possible points in space-time, and this is what this measure means. Okay, but beyond that it's just another leap. It's just a small leap in going from quantum mechanics to quantum field theory, where now I'm just integrating over some field that takes into account the quarks or the particles. And so it turns out that this lattice prescription is the only rigorous way that we have for defining what this path integral means. We don't have any other rigorous way. And in fact, the continuum definition is really a prescription. And if you can prove it and give a rigorous definition, you still will get $1 million prize. So if you want to make some money, not the easiest way, one of the smartest way though. And so the correlation functions, what they are is just a simple generalization of what I said in quantum mechanics, and they tell us how fields or particles are correlated from one point in space to another point in space-time. And they can give us, these correlation functions are remarkably useful because they give us access to the masses, the decay constants, form factors, scattering amplitudes of of hadrons or any particles. And so masses, decay constants, I mean, these are bread and butter properties, and then also, you know, non-trivial dynamical properties of how they structure and how they interact with each other. And so the simplest thing that you can have are what are called two-point correlation functions. And this is just a simple extension of what I said before. You have some field at some point in space-time, and then you see how it's correlated with another point in space-time. And so what you should think about, I don't know if I have a cartoon, is that this is creating, let's say, some particle, your favorite particle, and here I'm going to annihilate it some later time. And so this, you can imagine that the probability of creating some particle in some point in space, allowing it to propagate, and then annihilating at some other point in space, that probability for how it evolved from one point to another should have some information of its mass. It should have, you know, if I ask you, what is the probability that this particle will go from this point to another point, you better start asking me some properties about the, you know, of the particle. What is its mass? What does it look like? Does it have spin or not? You know, and so forth and so forth. And so that has to encode some information of the particles, and it does, and that's how we extract information about it. The way that you can evaluate this in the path integral representation is as just all possible integrations of these fields associated with this initial state and final state integrated over this weight and divided by some normalization. Okay? And so this is what you can evaluate in principle numerically. And so just a couple caveats, so a couple of challenges associated with this evaluation, and just to remind you why we have to sort to use something like lattice. So the integral and measure, well, it grows with the volume, right? It has this product. I have to integrate the value of the field everywhere in space-time, right? And so you can imagine if I have an infinitely large space-time like ours, this integral is going to be infinitely costly. And so it grows as I make my mesh finer as well, because I have more integrals. So more of these meshes means more integration. Bigger boxes means more integrations. And so the number of integrals grow with the volume, and inversely with the lattice spacing. Okay, so it is quite challenging. And maybe as a little test, I can ask you guys a question. So imagine that I wanted to do a scalar field in a volume with 10,000 points. This means that I would need to evaluate that many integrals, right? I want to have a space-time that is just 10 by 10 by 10 by 10. Four-dimensional space-time, and in each point is pretty modest, right? At each direction in my space-time, I have 10 points. And so I have 10 by 10 by 10 by 10 points to evaluate, and for each one of those, I have to integrate my field. Okay? That's what I have to do. And let's say that I'm going to approximate that integral by a mesh of 10 points. And so the question is, how many points would I have to add together to be able to evaluate this numerically? Ten to the 4. 10 to the 10 to the 4. That's right. Did I miss? I missed 1 point. Hey, do I have a typo? No, I do. Yep. Here, let's fix that. But yes, 10 to the 10 to the 4. Right, for each. So I would have to have 10 points for each mesh, or 10 points associated with each mesh, and I have 10 to the 4 points. And so overall, I would have to have 10 to the 10 to the 4. And modern day calculations are on the order of t, the temporal part, being around 200, and then L being in the order of 20 to 40 points. And so this would be astronomically large. And that is partly why we have to truncate our space-time. But also the reason why we don't have, this also explains why we can't evaluate these points directly, right? what we'd use instead are Monte Carlo, which allows us to sample over these configurations smartly. And so here's an example just to illustrate this, this counting of 10 to the 10 to the 4 in a brute force very explicitly for when we have just 2 points in space and we want to add up 3 points where the fields are just given values of 1, 0, and -1. So this would be something like an Ising model type. And so you have to evaluate the field over those 2 points in space and then I just would replace the first integral with the evaluation of 3 points. And then I would evaluate, so the function that I'm evaluating is a function of my 2 fields at the 2 points. So there. And so the first integral I approximate with 3 points. And then the second integral I approximate with 3 points. So 3 points for this guy, that gives me 3. 3 points for this guy, 3 points for this guy. And so I get 3 to the 2, which is consistent with what we found before, right? 3 is my mesh, and 2 is my volume. So in general, it would grow exponentially with your volume. And so this explains why, so the reason why this explains why this integral is hard, but it doesn't explain why we have to go to Euclidean space-time. And this is because if I wanted to do Monte Carlo sampling of this, I assume, are you guys familiar with Monte Carlo techniques, more or less? Somebody had a poster on it. Okay. So if you want to evaluate this integral numerically, you want to just randomly sample over these all the possible configurations. The ideal would be to use this as a measure, a probability density of the possible values that the field can take. Unfortunately, this comes with this pesky value of I, which makes my life very hard. Right? You can't use this as a probability density because it's not positive definite, and so we can't use this. And so instead, what we have to do is Wick rotate our theory. So we grab our time and we make it imaginary, which is why there's this. We went from something that the dot product of 2 things had a relative minus sign to something that now it doesn't have a minus sign, because we made I negative. And so what you have here in doing this is that this thing, I'm going to use a different color. By grabbing time and making it negative, then I have, or making it imaginary, I have now negative I squared, which is equal to -1. And so I have T and so the relative sign, I don't know if you can see it. All I'm saying is that by doing this, what is called a Wick rotation, I just get, now this comes in with a negative sign, and so this becomes negative T squared. And so I have now that there's no relative sign between time and space. And this overall, these factors of these negative signs that appear, you just have to treat them carefully, but they just basically get absorbed into different relations between Euclidean and Minkowski observables. Okay. And so here is an example of a 2-dimensional field theory where I have a scalar field theory. So this is some scalar field, so some scalar particle, let's say the pion. I just told you that every particle I can upgrade to a field, and this field would just be defining the probability of finding some particle at that point in space-time. And so this field has to have the same quantum numbers as the particles that I want to study. So if it's a scalar particle, it can't have any spin. And so the simplest thing I can think about is the pion not having any spin. And so this phi represents, perhaps the probability associated with the configurations associated with some pion. So here, all I'm saying is that you have the derivative with respect to T of this phi is just telling you about the time evolution of this field. This is telling you about the spatial evolution, and m0 is this mass, and then there's some possible interaction potential. And so Lagrangian is just kinematic piece, So this is a Lagrangian density. So it's just the density that appears inside of, if I integrate over all points in space over this, that gives me the Lagrangian. This is just a density of the Lagrangian density, So this is the kinematic piece minus the potential. Very similar to just simple Lagrangians in classical mechanics. And so by Wick rotating, all I'm doing is just showing that by changing t to negative it, I do a bunch of algebra, yada, 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 and I end up getting something that is positive inside with a minus sign. Okay, and so you can zoom in into this. I can post both slides, give you guys access to both slides so you can look at it. And so what this means is that I took my Minkowski action with this pesky I to something that is positive with a negative sign in front of it. And so now this is positive definite, and so I can use this as a probability measure and sample over these fields. So this is why we're doing everything in Euclidean space-time. Okay? And so the point is that in doing this rotation, I'm doing this rotation carefully to make sure that the physics doesn't change. Just like for people that are familiar with field theory, when you do Feynman diagrams, you Wick rotate to evaluate them in Euclidean space-time, where you can then use dimensional regularization and stuff like that. You're doing that Wick rotation, making sure that you don't sweep through holes or things like that. Yes? My convention so what Einstein taught us is that the dot product of any Minkowski vector with another Minkowski vector is a Lorentz scalar. So this doesn't change with respect to any frame. And you can check that this doesn't change with respect to any frame, because we know that the energy of an individual particle, according to special relativity, is equal to m squared plus p squared, square root it. And so this is the energy. And so I'm just putting in by hand what I know to be the energy of a single particle. I square this, and I have m squared, and that's supposed to be p vector. Oh, and I said c equal to 1, because I can't keep track of it. And then I have now just square the square root. I have m squared plus p squared minus p squared. Well, it is equal to m squared. And so there's the mass of that particle. So regardless of where I measure this, right? I could have measured this with boost equal to 0. With momentum equal to 0, and I would have gotten this. I could have measured this with momentum being 10 times m, and I get the same answer. So it doesn't. This is frame independent, and this only emerges if I have this nice low sign. And so Minkowski is a space-time where we can treat time and space together, but we have to treat them with care and separately. Okay. Okay. So then now we've done this rotation towards Euclidean space-time, and so what this buys us now is we can now evaluate this partition function, or this this partition function now in terms of fields. So again, it's still an integral, but now with a probability density that is positive and definite. And so what we do in our lattice calculation is that the first step is to generate a set of field configurations, so values for phi in space that are distributed according to this probability. So that's the first step in a lattice calculation. So you just generate some fields, and the simplest example of this is for example, an Ising model. So an Ising model, you can construct an analog of a field theory for the Ising model, where the spins are plus and minus, either plus or 1 or negative 1, and so you can just generate some field configurations that have some distribution associated with it. Then you have some ensemble of configurations, so phi 1, phi 2, phi to the n, that are are distributed according to this probability measure. And then the things that you can now obtain are, you can evaluate some correlation function or some function in general, whatever it is. We haven't associated any physics with it, that is dependent on your fields. Well, we can just evaluate the measure, the mean of it, by just what you would want to evaluate is just this evaluated inside your path integral. Well, then this is nothing more than just the value of this function evaluated for each one of these fields, and then divided by n. So that's just the average. And then you can propagate uncertainties and so forth once you've generated these configurations. Okay. And yeah, okay, so here's some discussion of how to generate these fields in a schematic way. You have some random fields configurations. You evaluate its action just by saying, okay, the fields are pointing in some direction. I evaluate those values into the action. I have some probability to accept that configuration, which is e to the minus the action, and generate some random number between 0 and 1. If this probability is close to 1, if it's close to 1, I'm more likely to accept it. If it's close to 0, I'm more likely to reject it. If I accept it, I put it into my ensembles. If not, reject it, I change the configurations, and then I repeat the process, and so forth and so forth. Okay, so this is perhaps one of the more challenging tasks associated with lattice calculations, but there's very clever people and very sophisticated algorithms that allow you to generate these fields. Should I maybe say, do you guys want me to continue along this path and give you some introduction to basics of QCD, or should I maybe?
Yes, for that.
You go for that? All right, good. Okay, so this might not be, I think here what I'm trying to say, again, I haven't looked at these slides in over a year, so here, just some words regarding QCD. So the QCD Lagrangian looks like this, and so embedded inside of the QCD Lagrangian, you have basically a kinematic piece. So this is just, so now instead of using phi for my fields, I'm going to use psi for quarks. And then inside of we use a mu for the gluons, and they're inside of this f mu nu. Okay, this is a function of a mu. So this looks just like QED, if you're familiar with QED, with electricity and magnetism, so it looks quite similar. And except that it's, instead of being a scalar field, these are matrices, three-dimensional matrices associated with color, with the fact that you can have three different colors, red, blue, and green. But the action is just a sum associated with this kinetic term for each one of the flavors. And the quarks can come in 6 different types of flavors: up, down, strange, charm, and bottom. And top is never used in any lattice calculations, as far as I know. And then you have the terms where you can have gluons are embedded in here. Inside of this derivative, you can also have couplings between quarks and gluons. And then you can have interactions between gluons and gluons of two different kinds. So here you can think of these are like Feynman diagrams, if you're familiar with them. And so the way you can think about these are, you have a quark that comes over and it hits it either gets struck by a gluon and it goes this way, or you can think of it as a quark that is propagating and then it emits a gluon and it keeps propagating in its merry way. Here, you can think of it in many different ways, right? You can have 2 gluons fusing into 1, or 1 gluon decaying into 2. Here, you can think of this as 2 gluons coming and scattering off of each other and going off their merry way, or 1 gluon decaying into 3, or 3 fusing into 1. You can rotate them each way and tell a different story, but they're all the same. Okay, and so this psi is a field associated with a quark. It now has spin, so it has a spin 1/2. It's not a scalar. That's okay. So it has an F, which tells you the flavor. Alpha is the Dirac spin index. This just means that it carries spin 1/2, so you can have up or down. So that accounts for 2 of the 4 indices. And then the other 2 indices are associated with parity, positive and negative parity. Or another way to think about it is a quark and its anti-quark. It has information about both, quark, anti-quark, and then 2 spins for each one of them. And so we just upgrade that into a space that is referred to as a Dirac space, because Dirac was the first one that wrote down the Dirac equation, obviously, which had this kind of structure. Okay, and then there's another index, which is a color index. And so this is a vector in color indices, so it can have 1, 2, and 3, and these are just associated with the fact that you have red, blue, and green colors. Okay, and then the gauge field, so the field associated with the gluons, is a vector. So this means that it's actually a spin 1 particle, just like the photon. And so the mu is this Lorentz index that I was writing over here. So it has 4 components, and they run from 1, 2, 3, and 4. And then it's a matrix in color. So it has an index C and an index C prime. So just a slightly more complicated story than this of scalars, but it's just matrices. They're just matrices. They're a little complicated, but we're already upgrading everything into a matrix structure so we can manipulate them numerically. So we just have to enhance the matrix size to be able to manipulate them. So nothing to be too overwhelmed by. And so then what you have to evaluate now are path integrals where you have a different measure for each one of your fields. So one for the gluons, and then one for the quark, and one for the anti-quark. Okay. So you just have to. So then now our fields live in a space that is as big. So matrices. These are matrices that are as big as our time, our volume, our flavor, our color, and Dirac. So these are fairly big matrices. That's why we have to use supercomputers, and we need a lot of smart people like you guys to write the code and run it and make it work. What do I want to say here? So the point of Lattice is that the reason why we go through all this trouble is because historically QCD has been outside of our axis, and we've had very minimal predictive tools. And here the beauty now is that if I have now QCD only has a finite number of parameters. So they're up the masses of the quarks and then some coupling. And so this coupling that couples quarks and gluons is the same coupling that couples gluons, and then it appears here squared. And so this thing, in principle, describes all of nuclear physics. And it only depends on the masses and then this one coupling. There's something fancy that occurs, which is, how do I tune this coupling? Well, the coupling gets tuned by the fact that in writing down the Cassini Lagrangian, there's no sense of energy scales. There's no sense of what do I mean by an MEV. That's absolutely lost, and this action doesn't know anything about that. And so in what you can do is translate this parameter G into an energy scale. And this is typically referred to as lambda QCD, which is just some number that is tuned to experiments. And so that's all it is. And this goes by some fancy name that is called dimensional transmutation, because you grab some coupling that is dimensionless and you transmute it to something else. Doesn't matter. And then what you can do is that once you've tuned these parameters, these ratios, you pick some value lambda, you tune these ratios, and you have full predictive power. You can determine everything out there. And so in Lattice, what appears is not this lambda QCD, but rather the lattice spacing. And so we can tune, just like it's done phenomenologically, we can tune these parameters of the different quark masses and the lattice spacing to some set of observables. And so here are some examples. So I can tune the up and down quark masses to give me the right pi 0 and pi plus mass. So the pi 0 is a mixture of UU bar and DD bar. pi plus only has d bar u. I can tune the strange quark mass by the kaons, the charm with something like j psi, which is a cc bar state. I can tune the bottom with the upsilon, which is just a bb bar state. And then the a I can tune with whatever other scale I want. And typically, one typical one is omega baryon. Why not? And so once I've tuned this, I have absolutely predictive power. I've tuned my theory, and then I have no more parameters to tune. And so I can't make any more tuning. This is quite different than any other theoretical tool that we've had in nuclear physics in the past. And in general, your observables will depend on the lattice spacing and volume and so forth. And I use this same trick. You guys have seen all my tricks. Okay, so I think this is where I left off in the other slides. Yeah, I think this is related. Yeah, this is going to be fairly similar to what I had on the other slide. So why don't you let me switch to the other ones. And how are we doing on time? Oh, we're pretty close to the stopping point. Well, how about this? Instead of switching just yet, I'm going to stop right here. And let you guys ask me more questions. And yeah. You don't. So lambda QC gets switched by a lattice spacing. So you have now. It's related to it. It gets replaced by the lattice spacing.
What's the relation?
I mean, it's a perturbative relation, right? So at the end of the day, you have some observable that depends on some lattice spacing that you can use. You have some observable that is so first thing you need to do is you've determined some observable in terms of that has a UV cutoff, which is a lattice spacing. So that is your UV regulator, and so then you have to match that observable. If it's renormalization scale, if it's lattice spacing, if it hasn't been renormalized, you first have to match that to your favorite renormalization scheme, say dimensional regularization, and there at that level, lambda QCD will emerge. But in general, neither one of them will appear. So if you have something that is non-perturbative, like pi mass, for example, lambda QCD doesn't appear there at all. Right? There's no sense of lambda QCD in low energy QCD. It is only a perturbative. It's only when we want to impose when we're forced to do a perturbative calculation to match to some phenomenological observable where lambda QCD emerges. So it would emerge at the level of matching perturbative expressions with lattice spacing and something else. Yeah.
So we were on this slide, talking about the QCD value.
This one?
Yes. So we're going over all the different workflows, specifically
the top is.
I don't know anything that uses the top fork, and then on the next slide, that's something very parameters include the top fork.
Oh yeah.
Why don't they use the top fork, and then why is it now occurring? Was that like the old
No, I don't think anybody. So simulating heavy quarks is actually quite challenging because they're really heavy, and so you need either really fine lattice spacings, or you need to have some non-relativistic prescription for how to impose those actions. So actually, there's quite a few people that use non-relativistic actions on the lattice. The advantage of that is that it allows you to simulate heavy quark masses. The disadvantage of that is that there's no continuum limit. There's no sense of how you can take the continuum limit. And so you're just matching things at that lattice spacing, so it's a regulator and you need it. The top work, the challenge is not that, is that it's so short-lived that it's the current constraints is that it lives shorter than it's allowed to hadronize. So I think this would be I don't know if there's any good motivation to use non-perturbative tools to study it. Yeah. Yeah.
Again, like how you measure the lambda QCD, you said that you need to measure by matching it to some parameter.
That's right. So in experiments, so I mean, so when you do perturbative QCD, you obtain, for example, some cross-section perturbatively. And there, when you're renormalizing your theory, so you get some divergences, and you, order by order in your perturbation theory, you have to remove those divergences, and something like lambda QCD emerges. And so it's some scale that is being imposed on you when you're renormalizing your theory.
Would lambda QCD depend on the scheme, RT scheme that you use?
Yeah, sure. Yeah, it depends. I mean, it's a renormalization scale and scheme dependent observable quantity. Yeah, so you're matching it to that. So it's not, I mean, just like, so you can think of, you can do in principle perturbative QCD with a hard cutoff, right? And so that hard cutoff is the inverse of the lattice spacing. You could have done that. And so then what appears is your hard cutoff in your calculations. There's really nothing that tells you you can't do that. It's just not a conventional scheme, and you don't have the nice properties of you're breaking Lorentz symmetry and so forth. So it makes it hard to do it, and it's not ideal for perturbative calculations. But there's really nothing that tells you you can't do that beyond that. So you had some other scale. But again, the power of renormalization is telling you, I'm gonna introduce some intermediate, thing like some renormalization scale or lambda QCD that I'm tuning then to match onto something physical. Again, the quark masses. I mean, you guys are fixating on lambda QCD, but the quark masses are unphysical, right? There's no sense of what a quark mass is because it's never free. So it's a renormalization scheme and scale dependent quantity. So even though lambda QCD might seem weird, I would argue that it's no weirder than the quark masses. It's just we have some we have some guess or intuition that we understand masses better than other things, but for things that are never free, you never have a free quark by itself, so you have no way to measure its mass. You're just tuning that parameter in your action at some scale, typically 2 GeV, so that you're reproducing some hadronic process. Is it renormalization scale dependent and scheme dependent quantity? So it's typically quoted at 2 GeV, I think. So yeah, so if you go to PDG, you would see the current estimates of the up-down strange and so forth, and there will be, so for those three, it's typically define add 2 GeV, while for the charm and bottom is a sign is given at its own mass. So it's a self-consistent equation. So you're evaluating the mass of the charm at its mass. That's its own mass. And same thing with the bottom. Okay. I realize we've gone on a different path, but hopefully this is still interesting. Okay, so, hopefully not. Okay, so, are people comfortable with everything we covered so far? Are there any questions that have arisen that need some quick clarification? All right, so you mostly believe everything I've said so far, which is good. So let me begin by just giving you a sense of what correlation functions look like in field theory, and I'm going to give you some, at least, intuition of how we extract the spectrum using correlation functions. And then I'm going to talk a little bit about how to interpret the spectrum, but given the mixed background, I might skip over many details so I can show you some numerical results that have emerged, okay? But, if we need to stop somewhere else, that's fine. Okay, so the simplest correlation function that we study and that gives us access to the QCD spectrum is one very much like the one that I covered in the context of quantum mechanics, where we measured one state at some one point in space-time, and then another one, the same state at some later point in space-time, and looked at the correlation between the probability of going from that point to the other one. But the analog of that in field theory is one that looks like this, where this O dagger is, so this correlation function is one where I have O dagger evaluated at 0 and then O at some later time. And so this O dagger, what it's doing is that it's creating a state out of the vacuum. Omega here is a vacuum, okay? So whatever it is, we don't know what it is in general, but it's just is the lowest state that is empty, no hadrons in your theory. And O dagger has the quantum numbers of a state that you want to study, say the pion or the nucleon. And so this just excites the vacuum, creates a state with those quantum numbers at the origin, and then you annihilate it at some later time t, and then overlap it with the vacuum. And so this is the simplest, and we call these 2-point functions because it depends on 2 points in time, 0 and t. We can have 3-point functions, 4-point functions, etc., etc. Okay, and so in the Heisenberg picture, so this is a way of saying instead of evolving states, we're going to keep the states defined at 0 time, and then we're going to evolve operators. And this is in contrast to the Schrodinger picture where you evolve states. And so these two pictures are equivalent, but it's useful to think sometimes in one picture versus another. And so in the Heisenberg picture, the states are time independent, but then the operators evolve in time. And they have these, this is now the time dependence, and the dependence of Minkowski versus Euclidean is absorbed in the operators. And so the operator at any other time is equal to the operator at 0 time with this evolution on the left and this evolution on the right. And this H here is a Hamiltonian of your theory. So the QCD Hamiltonian in this case. And T is your time. And so taking this for granted, what you can say is that if I then Wick rotate my theory into imaginary time, which is what we've done to be able to do Monte Carlo, t goes to negative t. And so instead of these oscillating functions, which oscillate with a Hamiltonian, now have exponentially damping or growing functions with my Hamiltonian. So that's the difference between these two things. And so what we actually calculate are correlation functions in Euclidean space-time, where inserting my operator that I wish to study at 0 time and then at some later time t. This I can identify in terms of the Heisenberg picture in Euclidean space-time, in this form. Okay? So I haven't yet shown how we can extract the spectrum from this, but hopefully these identities somewhat make sense. Okay? So then to make sense of how we extract the spectrum, what we do, what you can identify, what I can do is insert an equality. I can insert an identity, sorry. Do we have a eraser here? Oh, this. So we're going to introduce, I skipped one step there. So we're going to introduce the states n, which are eigenstates of the Hamiltonian. So I have some Hamiltonian for my theory. And these states n are just the eigenstates of H, so that when it acts on it, I get back the same state, and then I have En back here, okay? And so here I'm going to insert a complete set of states of n's. And so what I'm doing is that I'm saying 1 is just a sum over all possible eigenstates, and in such way that these are just eigenstates. I can pick any eigenstates of any operator. I'm just choosing them to be eigenstates of the Hamiltonian. And so by summing over all states, this is an identity. So that is just equal to 1, this sum. And so in the second step, what I've done is that I've used the fact that e to the th, let me just drive it. So I have OT, O dagger 0 is equal to sum over n, O omega, OT. And so here I've used this fact, this identity. Okay? And so then here, in the next step, I'm going to use the fact that the operators evolve with time like this. And then next, I'm going to use the fact that these are eigenstates of the Hamiltonian. And so, does anybody know how this is going to act? What e to the minus ht acting on n is going to be equal to? Yeah, it's just equal to e with where I replace h with en, this is acting on the nth state, times t. So now this is just a number. Right, this is an operator, this is an operator. Everything's an operator until I insert this. This is acting on the Hamiltonian, and then there's a number, and then I can pull it out. If this is not obvious to you, what you can just imagine is that e to the minus hn, well, I can just write some Taylor series. I can Taylor expand this, let's call it alpha, with some power, some coefficients, alpha, h to the alphath power. And then because it is acting on n, it's just going to give me h acting on n is going to give me en to all orders, and then I can resum that up. Okay? All right, so then this acts on omega, so it gives me back the energy of my my vacuum, whatever that is. So, and so that's how I got to this line. The e to the minus th acted on n, so I pulled this out. This one acted on the left-hand side, and it gave me back omega. And so then I pull that out, and then I assumed, I don't know if I said this, but I assumed that the vacuum has zero energy. And so that disappeared. If you don't want to assume that, then what you're extracting are energy differences with respect to the vacuum. And so one question that maybe would arise here, and perhaps it's not so obvious, is that here I've inserted a complete set of discrete states. And it is only allowed because I have an IR regulator in my theory. Because, and the reason, so maybe let me go to the punchline. The point is that I've used the fact that I live in a finite volume and my spectrum has to be discrete. So whatever the spectrum is, I know it has to be discrete because I live, if you put a single particle, any number of particles in a finite box, you're going to have, depending on your boundary conditions, it's going to have, you're definitely going to have some discrete set of states. There might be oscillatory, whatever they may be, but they're definitely going to be discrete. And so I've used that fact in saying that I have an identity over discrete states. In an infinite volume world, actually, you have a continuum of states, right? You can give two particles any value of energy continuously. And so in experiments, your cross sections are continuous functions of energy. And so this step wouldn't have been allowed in an infinite volume world. And so at the end of the day, what you have is that this correlation function is just a sum over exponentially decaying functions times some coefficients. And this exponential behavior with time is exactly dictated by the energies of your theory. And so if I have a non-perturbative way to evaluate the time dependence of these correlation functions, then I can directly extract the spectrum. And that's the basic idea that is used in lattice to get the spectrum. Any questions about this? Clear? Okay. And so in general, you have an infinite number of states contributing to your correlation function. So you have and just to maybe contrast this with the Minkowski case, if I had e to the minus it h, then I would have gotten the same functional form, but what would be different? What would be the difference in this correlator? Anybody? So here, let me write Euclidean is equal to e to the minus nt, and then these overlaps. I'll just have an exponential, yeah. But the same overlaps, the same coefficients. Same coefficients. Same spectrum too. Right? And so the same Hamiltonian. The Hamiltonian doesn't depend on time. The Hamiltonian is time independent. And so all the dependence in t is in right here explicitly. The operators are evaluated at the same time. You see that here I was careful to say OM, so Minkowski is equal to O, which has no M or E, times these time evolution operators. And same thing in the Euclidean. OE has these exponentials, but there's no E here. And so the operators are the same. The Hamiltonian doesn't care. The spectrum is the spectrum of the spectrum of the theory. So it doesn't care about how you access it. And so the point is that we can use Minkowski correlators to extract the spectrum. This would just be a bunch of oscillating functions. You know, you have a sum over different oscillating functions and so forth. While here, in this case, what you have are a sum over exponential decaying functions. But the spectrum is the same.
Is one a little easier to pull these coefficients from?
Yeah, I mean, exponentials, at least for low energies, is going to be easier. Yeah. But you don't know what the frequencies are. Yeah. Yeah. Yeah, we don't have a branch cut here. Yeah, it's a good question. I was actually going to talk about that later if I get to it. But what you have is the continuum of states are multi-particle. So there's a continuum where you have two particles or more going on shell, and that leads to a singularity in your correlators that is a square root singularity, and so you have a square root you have a branch cut starting at threshold. And you have it for every single threshold. So maybe we'll get to it, but if not, it's in the slides. Let's explain. Yeah. And so at least for one simple example of why exponential decays, I mean, at this point, we don't really have a choice, right? We've been forced to think about Euclidean correlators by having to do Monte Carlo sampling. And so what we want to do is get at physics. And so the simplest thing we can get is the spectrum. And so this question of whether it's easier to get the spectrum using real time or imaginary time is not quite, you know, we don't have that luxury just yet because we can't do Minkowski calculations. And so at least one simple limit you can convince yourself that is straightforward with Euclidean. You don't have to do anything too sophisticated, which is grab the correlation function that you're interested in and wait for a really, really long time. And so you have a sum of exponentials. And so at the end of the day, you have, you know, your lowest energy would be E0, and then this guy would be E1, and then this one would be E2, So these are what I mean by E1 and E2 is think of the energy being associated with some discrete set of states. I don't know what they are, but I'm just going to enumerate them by how much energy they carry. And so E0 is going to be my lowest energy, and because it's the smallest value in the exponential, that's going to be the one that survives the longest in time, while everything else is going to be exponentially suppressed. And so this motivates, you see a lot of lattice calculations where they introduce something called the effective mass plots, where what you're plotting is a correlator that you obtain for this kind at time t, and then you divide it by the same correlator at time t plus 1. You have this for many t's. So you take this ratio, and then you take the log of the ratio. And so you can see that if I take this limit, where t is very large, then that's what this arrow means. Then this is dominated by eta minus t e naught. The bottom is dominated again by that e naught, shifted by 1. You see the time dependence of these two exponentials cancels, and you're left with log of 1 over e minus e naught, which is this, and so that's just e naught. And so if you wait for really long times, this will plateau to some value e naught. You buy it? Okay. And so this is an example of this. This is results of some of my collaborators for the pion that has been given momenta of 0 units, 1 unit in the z-axis, 1 in the xy, 1 in the xyz. And these are in units of 2 pi over L, and I'll talk about what those units are and why they appear in a second. They're for a given box, and what you're seeing here are these effective mass plots. So this logarithm of ratios of correlation functions as a function of time, you see that they plateau to some value, and then that's fitted to for a range of energies, and you get a bunch of energy levels. Okay. So that's the simplest thing you can do for extracting a spectrum. So you're getting energy levels when the pion has no momenta, when it has 1 momenta, 2 momenta, 3 momenta. And here you're seeing some deviation from those plateaus in later times, and those are associated with the fact that these correlation functions are not just exponentials in time, but they're actually symmetric. I mean, for this case, they're cautious in time. So it's just a little deviation, but that's understood. Okay? Yeah. This is all lattice, yeah. This is all, yeah. So I think from here on, I won't show anything experimental observable, so everything is lattice. Yeah, so this is the pion mass times the lattice spacing for a world where the pion mass is approximately 400 MeV, because the lattice spacing is roughly this number. And so this is an unphysically heavy quark value of the quark masses. That's why the pion mass is approximately 3 or 4 times the physical quark mass. But nonetheless, I mean, I think it's a nice picture to illustrate how you extract the actual energy levels from correlation functions. Okay. What's that? Non-zero? Oh, because we're taking this ratio. So they're both decaying, but they're decaying at the same rate. Yeah, so you're taking a smart ratio. Yeah, I mean, if you plot it you can see it, yeah, seeing the correlation functions themselves is not a great illustration. You can take the log and then it would be a straight line. This ratio is a little more clever. There's different ways of representing correlation functions. Yeah. Okay, so this at least gives you a sense of how correlation functions are being extracted, how you can extract spectrum for simple cases, at least for the ground state, right? We had to do this large time behavior and extract this clever ratio of correlation functions to be able to extract this one energy level. And so the question that you might ask is, this is great for a ground state, but don't we want to have more information about many states? We don't want to be stuck in the lowest energy level. It's pretty boring. And this would go back to this question of, that I was proposing earlier of, if we want to study the isoscalar sector, there's many different energy levels that have the same quantum numbers. And so we want to be able to simulate and study these types of systems where there's many excited states. And so we had to do something more sophisticated. And so here's the result of some energy levels that have been extracted in this sector where the states have the quantum numbers of the vacuum. For now, this is just to impress upon you that these techniques are feasible, and I'll go into detail in how these spectrum can be understood and extracted and understood. And so here I'm showing you the spectrum. Here on the y-axis is the spectrum as a function of the volume on the bottom. So this is different volume. There are boxes of 16 cubed, 20 cubed, 24 cubed. Each one of these points is an energy that has been extracted. And this is for different boxes, different boosts where we're giving the system no momenta, one momentum on this and the z-axis, xy, so forth and so forth. The energy levels are all different, and they seem to have some dramatic volume dependence. So this is peculiar and interesting. And for comparison, here I'm showing the pi, the lowest energy that in experiments pi-pi's can have, that kk bars can have, and eta-etas can have. So these have the same quantum numbers as this. And so the questions that we'll think about is, first, how do we extract so many energy levels? This simple trick of extracting the lowest energy level is not going to be good enough. Then second, how do we give meaning to these energy levels? This seems kind of like a mess right now. There's no obvious story to tell here. And so hopefully we'll get into some of that. So first, let me address the first question. How do we extract so many energy levels? So the simplest answer, the first answer to this is, in constructing our operators, we don't really know what the wave function is for a pion, for example. We don't know. All we know is that it has some appropriate quantum numbers. And so we have a lot of freedom as to what operators we can use that have the same quantum numbers as the vacuum, as the pion, sorry. And so we make use of that freedom. There's many different ways that we can arrange quarks to have the same quantum numbers as the vacuum, and so that's one way to make use of that freedom. And so if, for example, I want to think about something that has the quantum numbers of the vacuum, so zero angular momentum and positive parity, then you can construct things that are, for example, conventional type operators that are QQ bar with some gamma function in between, some gamma matrix. This is just some matrix. But just so that they look like a quark and an antiquark tied up together to have the quantum numbers of the vacuum. I can also tie up a strange and an anti-strange, or a charm and anti-charm, right? So you can imagine these all have the same quantum numbers, and so in principle, I can tie them up and see them mixing between them. I can also include things that are tetraquark operators or blue ball-like operators. And then also, these also have the same quantum numbers as 2 pions or 2 kaons, right? Experimentally, the F980 decays to couples to pions and kaons. So you can also construct operators that look like 2 pions and 2 kaons and 2 etas, 4 pions, and so forth, that are mixed together in such a way that they have zero total momentum, for example. And there's many ways of tying these together so that they have the right symmetries or the right quantum numbers. And so this already tells you that you can construct a large basis of operators to be able to extract the spectrum. And so in general, what we do today is not use just a single operator, but we use many different operators. Let's call them OB and OA, and evaluate the correlations between OB and OA. Each one of these, the A and B are just different enumerations of my list of operators. Let's say I have 20. A and B are independently running from 1 to 20. That's all it is. It's just some number, okay? And the point is that the spectrum, if you follow the algebra that we went through before, and I erased it, the spectrum doesn't care about what operators I've used. All it has to have the same quantum numbers, but that's it. But the coefficients are different. And so now I'm gaining more information because I have many different operators, all with the same spectrum and different overlaps. And so now you can imagine using sophisticated linear algebra, and this goes by the name of the generalized eigenvalue problem, where you write a matrix of these correlation functions, where you have now not just a single correlation function, but you have a matrix of correlation functions which depend on time, which are your correlation going from 1 to 1, from 1 to 2, and so forth, until you go from n to n. And so you constructed a matrix, and so what you have to then solve is basically an eigenvalue problem for each value of time. And so you construct Vn to be the eigenvector of this matrix. Vn over here is the same eigenvector as matrix. And this is what you can show after a little bit of algebra is that the coefficients, the eigenvectors of this, or the eigenvalues of this coefficient of this equation are the energy levels that you're after. Okay. It's relatively straightforward. Implementing it is a little tedious, but it's relatively straightforward. So just to summarize, you've constructed many operators, you upgraded your matrices into your correlation functions into matrices, and so then you can extract many energy levels that way. One way you can think, if you want to think about it alternatively, is that you can having this information of many different correlation functions, they're all going to plateau to the ground state. And so you can construct what is the optimal value at large times of what operator is going to overlap with my ground state best. Once I have the optimal operator, I can subtract that from my correlation functions and go on to the next one, to a second state, and so forth, and so forth. Okay. So this is what, so these spectra have been extracted using a wide basis of operators. And so you can look at the overlaps and you can see that here what I'm showing you is little bars that suggest how much weight does each operator give to a given state. And so this is, the red are pi-pi-like operators, the grays are light anti-light, the greens are strange anti-strange, and then k-k-bar, and then eta-eta. And so you can look at each energy level and say, okay, this one looks like the pi-pi is very important, while for this one, the k-k-bar is really important. And this one is almost all eta-eta. And so there's something dynamical going on here. There's something interesting going on here. And it also makes sense if I remind you that here is a pi-pi threshold. So there's no pions, there's no kaons in this region that can be physical. They don't start until they're here. And so here there's a state that has somehow a lot of information about k-k-bar. And so that makes sense. While this one has almost no information about k-k-bar. Does that make sense, more or less? And another thing that is happening that I think is already you can see just by eye, if you zoom in into these three energy levels over here, they seem to be, as a function of volume, to be plateauing to some energy level below threshold. And so this is suggestive that this is, whatever the state is a bound state of two pions that have loosely come together and that lies below the pi-pi threshold. And it's a big object, there's a big fuzzy object that is being heavily distorted by our boxes. It barely fits in our boxes. So this is all to impress upon you that even just looking at these energy levels with a little bit of critical eye, you can see that there's already some interesting dynamic here I think maybe it was you asking about dynamics. I mean, this would be a dynamical type picture, right, where you can imagine ions coming together and getting loosely bound, and this is all just coming from seemingly static properties like the spectrum. So there's certainly something there, but it obviously starts to become very, very hard to decipher from this picture. So we need something more robust and solid or systematic to be able to get some information about the states over here. So before I continue, do you guys have any questions? Nothing? Okay. Okay, so let's assume that I've implemented all these techniques and been able to extract my energy levels. How do I make sense of them in general? So before I talk about these multi-particle states and scattering and all the stuff, we need to have confidence first that the energy levels that we extracted for a single particle does correspond to something meaningful. After all, we've done all these alterations to a theory. We put it in a finite volume, we introduced a discretization, et cetera, How do we have any confidence that we're recovering actual physics? Okay, so that's the first question we need to ask. So let me focus on that to some extent, and this was going to be a semi-detailed proof on a claim that for masses, if I consider energy levels below 2 particles, the masses of the states that I'm extracting as a function of the volume, I'm making an exponentially small error. And so we should have very strong confidence that those energy levels are actually corresponding to the energy levels of our theory. And so I might skip over a lot of details, but at least give you a warm and fuzzy intuition and then sketch out the details. And so on your free time, if you're interested, you can look at them over and you can write me or ask me questions about it. So what I'm going to do from this point forward is ignore the fact that I've done my calculation in a discretized spacetime. Just going to forget about that. Okay. Also, I've already hopefully convinced you that the Euclidean versus Minkowski stuff doesn't really matter. After all, you can think that the Minkowski versus Euclidean comes at the level of correlation functions. I've done some fancy work to probe out the spectrum of the theory from these functions, but the spectrum is the same for both theories. We can do a more rigorous proof, but hopefully that's sufficient for now. And so I'm going to ignore that stuff. And so I'm just going to think about Minkowski theories that are in the continuum limit that have been stuck in a box. And then furthermore, even though we're interested in QCD, I'm interested in the IR limit of the theory. So I'm interested in the IR limit of QCD, in the low energy region of QCD. And so in that region, quarks are not free. Quarks and gluons cannot live freely. They're always stuck and bound together into hadrons. And so although I'm interested in QCD, I can just think about a theory where I just have hadrons present. Okay? And so hadronic states are my degrees of freedom. And because I'm interested in the finite volume effects, like I said, those are IR effects. And so to first approximation, you can imagine I'm going to put a proton inside of a box, and I'm going to make that box periodic, right? That's one choice. I could have made other choices, but I'm going to keep it to be periodic. And so there's 2 ways to qualitatively think of the artifacts that we're making. One is that the nucleon energy is distorted by the interactions with its nearest neighbors. It's because it's seeing its neighbors that its energy is shifting. And so these are interacting. Does anybody know how nucleons interact at long distances? What is the long range part of the strong nuclear force? Okay, have you heard? Yeah, it's a Yukawa potential. So what does that mean? Yeah, what scalar field? Pions. Yeah, there we go. So what I have is essentially, I don't know why I'm struggling to make this box so much. Alright, so I have a nucleon, and it's interacting with its mirror image, and is interacting via pion exchange. So they're exchanging pions to each other. And so the shift in the energy in the Yukawa potential in position space goes like eta minus r times m pi, which is the mass of the particle that is being exchanged. So dr goes like that. And so the change in the energy of the nucleon from the fact that it's near another nucleon goes like e to the minus the distance between them times the exchange particle mass. But this distance, what is this distance in my box? No, I took the lattice spacing to 0, so I made it super complete. I put it in a box. The length of the box. Yeah, okay, cool. So they're separated by L, right? And so the shift is going to go like the separation between e to the minus the separation between them times r, the distance. So r, the distance between them, which in this case is L, times m pi. And so you're already seeing that the error that I'm making is order e to the minus m pi L. So that's already giving you a warm and fuzzy explanation of why these effects have to be small when m pi L is big, right? Then the other way to think about it is, which is the one that picture is illustrating, is that regardless of what boundary conditions I put in on my theory, I mean, whatever it is, this thing is going to have some radius. This nucleon is going to have some radius. And that radius, at low energies, the large distance bit of the radius, is dominated by the fact that the nucleon can emit a nearly on-shell pion that fluctuates and then it comes back up and it gets reabsorbed. And so the radius of all hadrons goes like 1 over m pi. And so the size, it's natural then that the radius over L is what emerges L over R is a parameter that tells you how bad of an error you're making, and this is m pi L, roughly, for hadrons. Just because the radius is associated with pions that are nearly off shell and propagating. So how big would the radius in the Carlo limit be for, say, a nucleon? What is the value of the pion mass in the Carlo limit? 0. So its radius should go like, if you buy the fact that it goes like 1 over m pi, it should go to infinity. So these objects get bigger and bigger and bigger as you go to the Carlo limit. And the opposite happens as you take quark masses to go to really large values. These objects get more and more compact. And so the error that you're making in introducing a box becomes increasingly less as you take the masses to be heavier, because they're just compact, tight objects. There's a lot of energy costs with having any quantum fluctuations. And so these things are just going to be, they're not going to be seeing anything in the boundaries of your box. And so this is all to argue how you would expect this to be small effects in the limit that m pi L is big. So it's a natural parameter that appears. Okay, so to make this more quantitative, I'll walk you guys through the steps. And there's really no simple way to do this without using field theory. So I'll walk you through the steps, and then you can do it on your own. And if you guys want me to stop at any point, just yell at me. Okay? So I thought it would be fun to derive this in 1+1 dimensional scalar field theory, in particular using lambda phi 4. So you have, here is a kinematic piece of the Lagrangian plus a dynamical part where you can have interactions. And this phi 4 term amounts to how many fields phi can interact in one point. So phi is a proxy for my pions. And so what Feynman taught us is, well, he taught us a couple of things. One of the things that he taught us is that we can grab complicated things and then just write simple diagrams that encode all the math. And so I find Feynman diagrams quite intuitive and quite nice. And so what this is a field where you have four of them coupling at one point, and then the coefficient is going to be proportional to lambda. Okay, so the probability of particles interacting on one point is going to be proportional to lambda. So a leading order in this theory, this is the scattering amplitude. This is how these pions or whatever scalar field I'm thinking about interacts. They interact in an energy independent way up to some coefficient lambda. And then the correlation function for a single nucleon, or a single pion, to propagate in momentum space is what is called a propagator. Hence why, makes sense. And it's just the inverse of this. It's just 1 over this thing in Fourier transform. So if I Fourier transform this, I have a derivative of P0 squared, derivative of the spatial part, and then I divide by that. Okay, so one thing that appears in field theory is that you have to integrate over all possible momentas. And so this intuitively, you can think about it, this appears when you're saying, well, my fields can interact by a contact interaction, but then I can also have, in quantum mechanics, you have to sum over all possible ways that particles interact. And so I can also have another interaction where they interact, and then they propagate, whoop, and then they interact one more time. This is allowed. Why not? Nobody's telling me it's not allowed, right? And then I can have one that interacts, and then decays to 2 particles, or it decays to 3 particles, and then it interacts with another one, and so forth. So I can keep drawing more diagrams. All the diagrams that are allowed that you can draw have this kind of vertex are allowed. And so you have to sum over all of them in principle. And so here what's happening is that you have, say, a particle with some momentum p, another particle with momentum p minus p. No, let's not do that. Let's call this one p minus k, and this one has k, okay? And so the total momentum of the system is p, some 4 vector p. So let p equal energy times the momentum, okay? And so then when they interact intermediately, I have to conserve 4 momentum, but that's it. So this can have momentum, let's say p minus L, and this will have L, right? The sum of these two, imagine time flowing this way. The sum of these two is p, which is equal to the sum of these two, which is p. And so why not? And what value of L should I pick? There's nothing telling me what value of L should I pick. And so that's why when you have this diagram, what you have to do is integrate over all possible values of L. There's a phase space factor of 2 pi times your dimensions, let's say. And then you have your propagator associated with this guy, L squared minus M squared. And then a propagator associated with this guy, P minus L squared minus M squared. And then you have to integrate, okay? It's a hard integral. In general, doesn't converge, but you have to do it, okay? In a finite volume, your fields things get a little start to get tricky because your momenta, does anybody remember what the momenta that are allowed in a finite volume are? If I make, yep, you ever had to drive that? Raymond, you're right. Yep, very good. Okay, let's say I have a wave function for a field that is just this. K times R. Okay? And so I want to impose, so there's some plane wave function for at some position R, that in that plane wave has momentum K. Okay? And what I want is my field to be periodic. And so let me think about one dimensions, okay? So I'm in a circle, and I'm gonna pick this to be length L. Okay? And so all I'm doing is I'm imposing that the field, my wave function, when I shift it by L, and it goes back to itself. Very natural, and that's what periodic boundary conditions amount to, nothing else. Okay? And so let me impose that. Let me say this thing has to be equal to, sorry, this should have been X. Let's just make this X. X plus L, right? This would make my field periodic. And so then I just put in the plane wave function here, and I shift it by L. And so I get that this is equal to e to the I k x times e to the I k L. And this thing has to be equal to this, which means that KL has to be equal to 2 pi times some integer. So it tells me that K is equal to 2 pi n over L. Okay? And so this means that wherever you had to integrate over momenta, you replace that integral, you have to replace it with a sum over your now discrete momenta, right? Because n can be negative, I mean, it can go from 0 to plus or minus 1, plus or minus 2, plus or minus 3, and so forth. So these are discrete numbers. And so then I replace this integral with a sum with a weight associated with the smallest values that I can give to n, which is equal to 2 pi over L times the smallest value that I can give to n. And so the 2 pi's cancel, and I'm left with L. Okay? So that's the last thing that you have to do is just replace these sums, these integrals with sums. Okay, so here's my broad sketch of how you would do this. So the way that you can do this to obtain the corrections of the mass as a function of the volume, you can look at the correlation function in this theory, and you would just draw all the full correlation function in a finite volume where you have all possible incoming one particle states and then one particle going out on the final. And so you would start by introducing your first propagator and then all possible loops and so forth. This loop you can evaluate, it has, this phase shouldn't be there, sorry. It's just it's an integral over the momenta, and then over this temporal momenta, and then sum over the discrete momenta. And so here I give you some steps on how to evaluate this. And they start from the Poisson summation formula. Have you guys seen this before? No? Yeah, some of you maybe. Okay. I put a proof on the back of the slides for you. And what it means, what it tells you is that the sum over a function of discrete values of the function can be written in terms of sums of the Fourier transform of that function. And so this is a useful way to replace an infinite sum with an infinite sum of integrals. Maybe not so useful. Sometimes useful. Sometimes it's a useful identity. And so here, again, I propagated this typo. This should be just 1. This shouldn't be, no, this is right. No, this is good. So here I've written the integral the sum that appears in terms of sum over integrals, and then I've isolated now the volume dependence that was over here before gets shoved into the exponential, and then the sum goes from 0 to negative plus or minus 1 and so forth. And so I can isolate the term that has no volume dependence, which is a term that has n equals to 0, and then the rest is just all the n not equal to 0. And so then I just have to, if I want to understand the volume dependence, all I have to do is just evaluate this stuff over here. And so here I do a bunch of identities and basically show that this correlator can be written as a propagator that has p squared, and then here is something that is just purely infinite volume physics, and then something else that is a shift. And so this shift is associated with the corrections of the masses of hadrons in a box. I'm going to skip a lot of this stuff because even though it says that it's easy, maybe it's tongue-in-cheek. I don't know. Anyways, so here's a few number of steps that will get you to the evaluating that this integral, after a little bit of algebra, after just 6 simple points, is equal to an exponential with m and l, which is what you expected. Okay? So if you're feeling like you don't have enough to do tonight, you can check all these steps and send me notes on whether you found a typo or not. And so the punchline is that after just a little bit of work, the masses that you obtain in a finite volume are equal to the masses you obtain in an infinite volume, plus a correction that we've evaluated explicitly here. And so now if you do a calculation with ML being sufficiently big, you can rest assured that you're extracting something meaningful. So here's an example of this being implemented. So here's results of this calculation that I mentioned earlier, where the mass of the pion has been determined, and this has been determined for 3 different volumes, increasingly big on this axis, where the volume goes from m pi L 4 or so to 5 or so to almost 6. And you see that there is some volume dependence, but it becomes increasingly mild, and so you hope that you've reached some level of convergence here. And so this is the limit. You know, if you were to compare with experiments with this, okay, obviously this is not the right quark mass, this is fairly heavy, but you know, the point is that this you can't compare directly with experiments. This one maybe, this one definitely. And so that's the idea. Okay. So it turns out, and here what I want to say is that there's some general statements that one can make as to why this turned out to be true, and you can solidify them in general for not just masses, but for also form factors and many different functions. And so maybe at this point, I'll stop for a second and see if you guys have any questions. I know I've glossed over a lot of points, but I figured it would be less miserable than walking you guys through all that stuff. So you can ask me about Jazzy too. It doesn't have to be physics.
Where is she?
Where is she? She's at home. It's a Jack Russell. Yeah. She's 14, going on 60. She's a grumpy old lady. All right. So this was going to be the beginning of part 2. And so the last thing that I wanted to talk to you guys was about doing scattering on the lattice. And you know what? I'm going to skip this derivation because it's only slightly more painful than the last one. So I have a quantum mechanical derivation actually that I think might be more useful. I haven't thought about this in a while, but I also don't, yeah. Anyway, so instead of doing the field theoretical derivation, let me give you a sketch of the quantum mechanical derivation in 1 + 1 dimensions. It has the same punchline, and it agrees, which is good. So imagine that what I want to do is a scattering of 2 particles, okay? And so the way that we define scattering. So let me see, 2 particles in a plane wave, center mass. Very good. Okay, so the way that we do scattering is you have 2 particles coming in, they interact in some finite range potential, and then what that does is that it shifts the phase of your plane waves. So imagine I have plane waves coming in, and then in the center mass frame, the potential has some finite range, and so whatever comes out in any one of the directions is going to be shifted by some amount, and that amount encodes the interactions that happen locally, right? So that's the basics of scattering in quantum mechanics. And so in the center mass frame, I get this, and so you're imagining they're coming in with some momentum p, and x is the relative position between the 2 of them. And so what you can do is find solutions in 1+1 dimensions where for the outside the potential, so if I just impose that the wave functions are most shifted by a phase shift and some unknown parameters, for x values that are behind less than the center of the potential, and x values that are greater, this is a typo, then I just get these 2 conditions. I get that the wave function in general, I can write it in terms of up to some coefficients a and b. And so if I impose that the wave function is symmetric, and this would be for identical bosons, let's say, then that puts some constraint on the coefficients, and I find that the allowed wave functions have to be cosine p times the absolute value of x plus the phase shift. Okay. And so more explicitly, this is what that means. It means that if I'm below x 0, and I think this is again typo, I just propagated this typo, x greater than 0, it has to be this, right? This has to be, if it's positive, then it's going to be a positive thing. If it's negative, this is also going to be a positive thing. And then also, I can look at the derivative. I want to require not just the wave function itself be symmetric, but also a derivative. The whole wave function has to be symmetric. And in this case, the first derivative is sufficient. And so by requiring that, I have that the first derivative of the wave function amounts to this, and then I have a negative sign on the other part of on the positive x value of the wave function. And so this is just reminding you of 1+1 quantum mechanics and where does the phase shift come in. It's just encoding the dynamics that are happening in the short distances that we can't actually probe. All we can probe are the long distances of the states, and we've isolated the wave functions, and notice that the wave functions that were oscillatory are still oscillatory but shifted by some amount. And that amount encodes the fact that they went through some potential. That's the basic idea of phase shifts. Okay? And so then, now the only thing that you have to do is imagine, now I'm going to think about what happens when I put these particles in a box. And so I have them in some finite volume, and I'm going to make that volume periodic, and so it just amounts to being in a ring. Fair enough? And so I'm going to require that these are sufficiently separated so that they're fairly isolated. So that for large x, they no longer are near each other, they don't feel each other's presence. And so the wave functions that I wrote down before should apply, should describe the system fairly well. And you can believe that, right? I mean, if I make this ring really big and they're sufficiently separated, they're not going to feel each other. And this is also related to the fact, this also should flag a little bit of warning that here I'm making a strong assumption. And the assumption that I'm making is that the potential is finite range. But electricity and magnetism, the potential is not finite range. And so this already tells you gives you a little bit of taste of why putting QED in a lattice does not make, it's a non-trivial issue. This is one of many things that appear. And the thing that you can imagine is that creating a photon is infinitely cheap. And so they can propagate and sample our boundaries. And so putting QED on the lattice is very hard for that reason and many others. And so here I'm assuming that the potential is finite range, and this is safe by the fact that the lightest particle that the hadrons emit is a pion. And so again, while in QED, the lightest particle that the particles emit is a photon, right? And so the photon has a mass 0 that makes this non-zero, that makes QED not have a finite range, while in QED at long distances, the lightest thing you can emit are pions. And so there's the probability for you to be able to observe a physical pion at large distances decays exponentially. Going back to this picture by Yukawa. And so, okay, so I've made an assumption that as I separate these two, the potential is finite range, they don't see each other anymore, and so using these asymptotic wave functions that exist outside of the range of the potential is a good approximation. And so then all I have to do is just grab those wave functions and impose periodicity. And I'm going to impose periodicity by requiring that, you know, just saying the wave function is equal to the value of the wave function. So the wave function at L1/2, so I just pull, you know, I separate them by L1/2 and then L minus, or negative L1/2. So the distance between these 2 points is L. And so requiring these to be the same just amounts to this condition in the wave function. Okay? That's not enough. So I also impose that the derivatives are periodic. And so now I have two equations that I can evaluate. And so what this tells me is that the argument of this thing has to be equal to pi over n, or pi times n, some arbitrary integer. And so then I get this condition. And this condition actually is this is, if you go to the slides and you see the field theoretical derivation that I present, is many, many, many times longer than this, but it arrives at the same equation. And this equation is quite amazing. It's quite powerful because what it's telling you, and let me skip to what it's telling you, forget about the line above. I just skipped so I can show you some plots that illustrate this. What it's telling you is that if you determine the spectrum in some box L, I can match this to some infinite volume phase shift at that value of the energy. And so although I can't do scattering, where I require this definition of asymptotic states, I can do this by matching my finite volume spectrum onto infinite volume observables, having done some quantum mechanical gymnastics. And qualitatively, what you can imagine is the shift in, you know, scattering in the infinite volume world comes from the fact that I have a non-zero potential between coupling my initial states, which is over here, has some initial states, and time is flowing this way, and I have some final states. And so I have some potential that transitions me from my initial state configuration to my final state configuration. And so this is correlated to the fact that I have a potential, okay? So I have some interactions. Well, the shift in my energy levels, let's say that I measure some energy in my lattice calculation. Well, I can compare this, say, to just having two particles inside of a box with no interactions to them. If I find this to be non-zero, well, you can just, using quantum mechanics, that will tell you that this has to be tied to the shift, to the expectation value of my potential from my free states. This is all to say that the shift in energies inside of a box are associated with the potential, just like the scattering amplitudes are associated with potentials. And so since these are correlated, that tells you that these have to be also correlated. Okay. Okay, so maybe to drive this message even further in, because it turns out to be very powerful and useful over and over again. I mean, our calculations rely on this observation. Here, what I'm going to first do is the phase shift, again, is encoding how much particles are interacting. And so if I set them to 0, that tells me there's no interaction between particles. They're just free, they're just propagating their merry way. And so I can set that to 0, and then determine what the spectrum is inside of a box. And you see I get that P is equal to 2 pi n over L, which is exactly what we said was the spectrum of a particle inside of a box. But here what we're talking about is the relative momentum between particles. So I was just saying I have some particle with 2 pi n over L, and then the other particle has to have negative 2 pi n over L. And so each one of the particles just has the free momentum that is allowed. So it is, it makes sense. No phase shift, free spectrum. So that hopefully makes sense. And so these dashed lines are what the spectrum would be just by plugging in this equation using P is equal to 2 pi n over L, and then just evaluating the energy of the two-particle system, which is just equal to I'm sorry, I keep making you get up, which is equal to the momentum, the relativistic energy for each particle, both having the same mass. I have to add the energy of one and the other, and so I'm going to multiply this by 2. Okay? And so that's what I'm plotting. It's just, and you see that they're all decaying with the volume. Does this make sense? Yeah, sure. The momentum is decaying with the volume, so the energy is decaying to the volume, and they're all going to the lowest energy, which is just the mass of the two particles. And so here, now, what I'm doing is I'm grabbing a phase shift that I'm just picking to be whatever I want. This is actually called a Breit-Wigner. So there's a Breit-Wigner amplitude or phase shift, where the phase shift is 0, and then it grows rapidly at some point, and this you can associate with the presence of a resonance. Yeah? Mm-hmm.
Shouldn't there be some kind of binding energy or like favorability for them to be together?
Yeah, but if there's no interactions, then I mean it depends. You're right. It could be. So what I was plotting there is the spectrum with no interactions. So the lowest energy that two particles that don't interact can have is just a mass of one and a mass of the other. The fact that they bind is because they're interacting and there's a potential that is attracting them to each other. Yeah. Okay. So then here I just grab some phase shift, whatever it is, doesn't matter. And then just the point is that it encodes dynamics. And this is the simplest observable that we can extract associated with that tells us about the dynamics of particles. And so I can put this into that equation and now have some function of energy, which is this one over here. And then I have to solve for, if I solve them for the momenta that satisfy this equation, I get these blue lines. And you see the blue line is right on top of the yellow line over here. This is a relatively low energies, right? So the energy here is like 400 MeV, and you see that in the 400 MeV region, this blue line is consistent with 0. This region, right? And so that's consistent. There's no interactions here. The phase shift is 0, so that's telling me there's no real interactions. And then in that region, in the spectrum, I can't see the difference between free and interacting energy levels. As I go here in the 6 to 1000 region, this is very far from 0. right? So around here, you see it's very far from 0. And so if I look in the spectrum around 800 MeV, you see there's a big gap between this blue line and this dotted line. So that's telling you, that's consistent with this, right? There's strong interactions over here. This is really far from 0. That's telling you that the particles outside of their potential have been shifted quite a bit. The wave functions have been shifted quite a bit. And so that makes sense, but it's also telling you that here there's some big gap between the free and the interacting energy levels, so it's self-consistent. And then again, as you go to higher and higher energies, they start to get closer together, and that's because you're approaching 180 and you can't really tell the difference between 180 and 0. Cool? All right, but what we do in the lattice is not this. We don't grab some phase shift and determine the spectrum. What we do is the opposite, right? I told you all this trouble that we have to go through to extract the energy level. So this is mimicking what we do in the lattice. You do some horrible calculation to get at correlation functions. You extract these exponential decays in the correlation functions as a function of time. You extract many energy levels in a given box, and you get these energy levels over here. And so what you then do is you grab these energy levels, you put them into this equation, you say, aha, I know this energy level, that means I know Pn, I know what box I use for my volume, and so that gives me a constraint on delta. So I put it over here, and then I get that delta is 0. I do it for this other energy level, same thing, I put it over here, that gives me another point. Delta corresponds to this value. So this guy corresponds to this guy. This guy corresponds to this guy. And so forth, and so forth. And so I get a constraint for the phase shift at that one energy level. Then you can dial your box. Okay, you do that for all the guys. Then you can dial your box, and you do the same exercise, and you see you get more and more points. And so slowly this starts to look like what you do in experiments. In experiments, you can tie the phase shifts to cross-sections, and so this is equivalent to extracting a cross-section at this point, having just extracted energy levels. Okay? Pretty cute, no? Any questions? No? Yeah? Here you mean? The phase shift, yeah, I mean it's very tiny. It's close to 0 here. Yeah, it just happens to be. I just picked some phase shift, which is associated with a Breit-Wigner, so the erase, yeah. So, have you guys heard of Breit-Wigner amplitudes? No. Let me go back. I actually have some illustrative. Yeah. Okay, here. It's freaking. Okay. Okay, so just here's an example, which I skipped over, but maybe I should.